Good morning, freshman physics students. Today, I'm going to teach you how to mark the amplitude and wavelength on graphs of both transverse and longitudinal waves. And in order to do this, I'm going to show you some actual waves that students in previous years have made and show you how to label those.
Two students are going to take.
So in this video, we have the students taking a rope, and they're going to try and make some nice waves with this rope. Now, they're not going to be perfect, but you get the idea that they now have some waves. Another student videotaped the wave with an iPad. Then what they were able to do is to move along that video until they can take a screenshot of one good wavelength. So they're going to hold it, they're going to pause it when it gets to one good wavelength. Now you'll see here that they have one nice wavelength that they have taken a picture of. And you get the idea of what was causing the wavelength by the motion that the student was doing to make that wave move up and down. The actual rope was moving up and down while the wave was moving across the floor. Again, you'll see that perpendicular, that's a transverse wave or a T wave. Now, as we look at this, one of our homework problems was asking you to find the amplitude and wavelength of, or to draw a wave and show the amplitude and wavelength. So this gives you an idea of how to do that. So if this is your wave, one wavelength, we can say that it is crest to crest, or trough to trough, or we could say that it begins here and ends here. Now you notice that the distance from crest to crest should be the same as the distance here. This is our wavelength. And if we were to measure this in meters or centimeters or any units, that could give us the length of a wave. So if our wavelength was supposed to be, say, 1 meter long, then from crest to crest would be 1 meter. And also, from the beginning to ending as it crosses the resting point would be the same amount. It would also be 1 meter. If we had continued, if this had been a better wave, we could also have said it was trough to trough. And again, that's also one wavelength, which should be 1 meter. Now, on this same thing, how can we find the amplitude of the wave? Well, remember, the amplitude is either half the distance from crest to trough, which would this would be the crest to trough, so we would take half that distance. Or we could say that it is the distance from the resting line to a crest. So this is the amplitude. Let me take this off so it's more clear here. The amplitude, if we take it from the resting line to a crest, that would be the amplitude. So let's say the amplitude was supposed to be 300 centimeters. Now let's say that let's change that. Let's say that this is 1 meter. This looks like about a fifth of that. So how much would the amplitude be if it's a fifth of 1 meter? Oh, that would be about 0.20 meters or 20 centimeters. So this is the way you would label a transverse wave. Now let's look and see how we would label a longitudinal wave. For a longitudinal wave, we're going to consider a slinky. And again, we have our students with the slinky. And this time they are going to make longitudinal waves. They did a video of this. They recorded until they found 2 good compressions, and then they paused their video. Then they paused their video on their device so they could now use this to identify the parts of this longitudinal wave. So if we look at a longitudinal wave, some definitions that you need to know is compressions and rarefactions. Compressions are where the wave is compressed or scrunched together. So we have a compression here and we have a compression here. That is where the actual wave is. The compression is showing the amplitude of the wave. So the more length you have here, the more amplitude you have. And these type waves can take place in air, like a sound wave, or obviously in slinkies. So the amplitude of this longitudinal wave is the same as the length of the compression. Now, where it is not compressed, you'll notice the slinky is spread apart, and that is called a rarefaction. It's almost like it's rare there. If that was air pushing, that's where the air is rare. Where the compression is, that's where the air is pushed together. So you also have a between area between the compressions, and that's where your rarefactions are. The rarefactions are between the compressions. Now, to find one wavelength of this, you can either measure the middle of your compression to the middle of your next compression, and this is your wavelength. Or you could do the beginning of the compression to the beginning of the next compression, and that is the same distance. That is also your wavelength. And again, you can measure this in meters, centimeters, kilometers. You can measure this in many different types of lengths. One more thing I want to point out to you is that the longitudinal wave, I'm going to erase all this just so it doesn't look like such a mess. In the longitudinal wave, the compression or the wave itself is going along the same direction as the motion. The person was pushing the wave in one direction, and the wave was moving that same direction. Actually, I believe in this video it may have been going opposite of that. But the idea here is the wave is going along the same direction as the motion. So longitudinal waves go along the same direction. Thanks for listening today. Hopefully this has been helpful.